Hi, welcome back. We are going through the properties of determinants. Let's look at this particular property. If two rows or columns of a matrix are identical, then the determinant is 0. What's the meaning of that? Let us say, let's take a matrix. We'll say A11, A12, A13. Let us say the second one is also same, A11. Okay, A12, A13, or maybe instead of confusing you, let me take something else. Let's take a matrix A1, B1, C1, A2, B2, C2, A3, A2, B2, C2. Now you can see in this matrix two rows are identical. We are going through this property. If two rows or columns of a matrix are identical, then the determinant is 0. That means the determinant of this particular matrix A1, B1, C1, A2, B2, C2, and again A2, B2, C2 is 0. Okay. To make it very easy, what I will do is I will take the row which is not identical and try to use it to find out the determinant. But you can take anything. You can take anything. You can directly actually calculate. You can prove that the determinant is nothing but equal to 0. So let's go ahead and do that. Let's put down the signs plus minus plus. So I'll have plus A1 into, if I remove this row and this column, I'll have B2C2 minus B2C2, which is 0. Then I'll have minus B1 into A2C2 minus A2C2, again which is 0. Then one more I have is plus C1 into A2B2 minus A2B2. That's also equal to 0. So you can see 0 plus 0 plus 0, the determinant is 0. Now what I suggest you is, instead of taking this, suppose I take A2 B2 C2. Let us say that if I have taken this and see if you calculate the determinant, you will get 0 or not. I have checked already, you will get 0, but just try a look at that. Okay, let's move to the next property. Next property is, if each element in a row or column of a square matrix is sum of two numbers, then its determinant can be expressed as sum of two square matrices. Like, I will show it to you. What's the meaning of that is, now suppose you have a matrix like this. Okay, maybe I need a little bit of more space. Okay, let us say A11, A12, A13 plus X, A21, A22, A23 plus Y, A31, A32, A33 plus Z or Z. Now you want to find out the determinant of this. You can actually try this out. This determinant of this particular matrix is nothing but equal to, you can actually write it as two matrices. How you can write them as, you can write it as A11, A21, A31. To simply understand, the matrix which is written as sum of two numbers, that column or that row will not remain the same. Remaining will remain the same. That means remaining two columns. Here I am changing the column. Here actually I have a column which is expressed as sum of two numbers. So now my first matrix will have the remaining two columns as it is, that is A12, A22, A32, and I'll have here A13, a part of it, A23, A33, and the other matrix will have the same columns for the remaining ones, that is A11, A21, A31, A12, A22, A32. After that, I'll have X, Y, and Z. Now, how to prove this? Very simple. Very simple. How we will prove this is, you can actually try it out, but I will tell you how to do this. Okay. Now, where you are going to write it, right? Let's take it as a candidate to find out the determinant. That means I am going to take this particular column to find out the determinant. Okay. Right. Now see here. Now, very clearly you can see that other than this third column, remaining two columns remains same in the next two matrices. What exactly is the meaning of that? The meaning of that is the cofactors will remain the same. What's the meaning of that is, if I take this particular element A13 plus X into, let us say, what is the cofactor of this element? What is actually cofactor of that? Minor. So plus minus plus minus 1 to the power of I plus j, that is positive 1, multiplied with the cofactor is nothing but the matrix obtained by removing that particular row and column A21 A32 minus A22 A31. Okay, let us say that's nothing but equal to A13. Okay, I will remove everything and say element into cofactor. Cofactor is A13. Now you go to these two cases. Now you come to these cases. You can see that this element, first element, how you can write it as, what is the determinant if you want to find out? First element of this matrix will be A13 into A13, same thing, A21 A32 minus A22 A31. Why? Because as I said, remaining columns are untouched. You are not touching them. That means the cofactors will remain the same. This is nothing but equal to, and coming here you will say that that's nothing but equal to X into A13. So that tells you very clearly what it tells us. It tells us very clearly that if a particular row or a column can be expressed as sum of two numbers, then you can actually separate them into two square matrices of the same order. If it is 3 by 3, it's a 3 by 3. Now only the point you have to remember is, other than particular row or column, remaining values will remain the same in the two matrices. So that's a property what we have learned. What's that property? If each element in a row or column of a square matrix is sum of the two numbers, then its determinant can be expressed as sum of two square matrices whose columns or rows will remain the same for that particular, other than that particular column or row where it is expressed as sum of numbers. Where it is expressed as sum of numbers, you will have that column divided into first part in the first matrix, second part in the second matrix. Like if you take here A11 A12 A13 plus X, A21 A22 A23 plus Y, and A31 A32 A33 plus Z. Now when I want to find out the determinant of this, what I can do simply is, I can divide this into two parts where the first two columns will remain the same. The third column of the first matrix will be first part of it. The third column of the second matrix will be second part of it. Remaining columns remains the same. I hope you understood that. If not, you just try it out. Just to try to find it out. By expanding it, you will see that it clearly works out. Let's move to the next property. Okay, this is a property which we are going to see. This is sixth property. If each element in a row or column of a square matrix is multiplied by a number p and added to the corresponding element of another row or column of a matrix, then the determinant will remain the same, or the determinant of the resultant matrix is equal to the determinant of the given matrix. What exactly is the meaning of that? Square matrix, if each element in a row or column of a square matrix is multiplied by a number p and added to the corresponding element of another row or column of a matrix. Let's try to simplify this. Let us say that this is A1, B1 C1 A2 B2 C2 A3 B3 C3. There is a matrix. Now what I am going to do is I am going to multiply this particular row with a value k and try to add it. If you remember, we are saying R2 is assigned R2 plus R1. You remember this type of transformations we are using it? We are using it because we know that by this the determinant will not change. That's what we are going to see now, why it will not change. If I apply, let us say that I am going to multiply this with k and add to that. So what it will become now? It will become A1 B1 C1, then it will become A1 plus k A2 B1 plus k B2 C1 plus k C2, and the remaining will as it is will be A3 B3 C3. Now just now we have learned that whenever you see that a particular row or column can be expressed as sum, then you can actually write them into two parts. How I can write it? I can first write it as A1. Remaining, here we are working on row, so the remaining rows will be the same. So I can just go ahead and write them as A1 B1 C1 A3 B3 C3. Now this is the row which I want to divide. So first I will keep A1 B1 C1, and if I come to the next one, I'll have K A2 K B2 and K C2. Hi, there was a small typo, so I just fixed it. What we are trying to do here is, if each element of a row or column of a square matrix is multiplied by a particular constant k and added to the other row, like suppose let us say A2 becomes A2 plus k A1, or R2 is given as R2 plus k R1, okay, then the determinant value will not change. Why? Because just now we have learned that we can actually divide this into two matrices, so that now we are working on rows, so the first row and third row will remain the same, and the second row can be divided into two matrices. First will take A2 B2 C2, and the second matrix will have second row as KA1 KB1 KC1. Now you know this is nothing but equal to 0. How we know? I can take k out. If I take k out, two rows are identical. We just have seen that if two rows are identical, then this matrix determinant will be 0. Now that's nothing but equal to whatever the matrix we want. So by this we can see very clearly that whenever you are applying the transformations, like R1 is assigned as R1 plus R2 plus R3, or R2 is R2 plus KR1, or R2 equal to minus R2 plus KR3, whatever you are trying to do, okay, on those transformations the determinant will not change. So we can use the transformations and try to simplify the problem. That's the whole idea. Okay, we'll do some more properties, yeah, and we'll wrap this up. Okay, so the sum of products of elements of a row with the cofactors of corresponding elements of another row of a square matrix is 0. What's the meaning of that? Suppose you have a square matrix with elements A11, A12, A13. You have A21, A22, A23, A31, A32, and A33. Okay, there is a matrix and you want to find out the determinant of it. Okay, now what you will do generally to find out the determinant? You will take A11, then you will find out the corresponding cofactors. Okay, now suppose you have taken the elements from one row and the cofactors from the other row. You just try to do that, then you will see that actually it will become 0. Let us see how it becomes 0. Let us say that we want to find out the second row. Let's say that we want to find out A21 into A11 plus A22 into A12 plus A23 into A13. Okay, right. Now A21 into A11. What is A11? A11 is nothing but A22, A23, A32, A33. Then after that I have A22 into A12. A12 is nothing but equal to A21, A23, A31, A33. A21, A23, A31 and A33. What's the next one? Plus A23 into, let's multiply that with the cofactor of A13. Okay, what we are trying to do now, instead of doing it the product of the element with corresponding cofactor, we are trying to find out the element with the corresponding element of other rows cofactor. That means if I am now A21, I should multiply with capital A21. Instead of that I am multiplying with cofactor of A11. So it is A21, A11 plus A22, A12 plus A23, A13. Now what is A11? A11 is nothing but A22, A23, A32, A33 matrix. That's the determinant of that square matrix, 2 by 2 matrix. Similarly, A12 is nothing but A21, A33, A31, A33. Next, what you have? A23. If you go to A23, you have to multiply with now cofactor of A13 element. That's nothing but equal to A21, A22, A31, A21, A22, A31 and A32. Okay. Now how this matrix looks like? Let us see this. Now how this matrix looks like. How you will have element. Now your first element will be A21 because you are multiplying that. Now your second element will be A22 and your third element will be A23. Okay, right. Now when you are multiplying with A21, you will have A22, because you know when you are multiplying you will remove the column and row and the remaining square matrix will be nothing but A22, A23 and A32, A33. Okay. Now if you go to A22, you will remove that row and that column. You should have A21, A23 and A31, A33. This is how your matrix should. This is nothing but equal to determinant of this particular matrix. Let's look at this one. A23. If you take it out, you will have A21, A22, A31, A32. Now you can see that these two rows are identical. If these two rows are identical, then the determinant will become 0. So you can see now that instead of you multiplying the element with its corresponding cofactor, you multiply with the same corresponding with the corresponding element of another row. That means if it's a first element or second element or third element, but not with that row, with the another row, then the determinant, the sum of the product of them will be 0. Why? Because they will be identical rows or identical columns. Okay, right. We have some more properties here. I actually request you to have a look at this. For any square matrix, det of A equal to determinant of A transpose. So you can take any matrix and you know how to transpose the matrix. You find out the determinants of both of them. They should be equal to same. And not only that, determinant of multiplication of two matrices is nothing but individual multiplication of their determinants. So determinant of AB equal to determinant of A into determinant of B. This also give you another property, the determinant of A square or A to the power of n is nothing but equal to determinant of A square is nothing but equal to determinant of A into determinant of A. You can write. Similarly, A to the power of n equal to determinant of A into A n times. Now, the last one is if A is a triangular matrix. Okay, we haven't discussed about this, right? What's a triangular matrix? A triangular matrix is a matrix which is having, okay, suppose you take any matrix, right, where you have I equal to j, those elements, let us say these elements like A11, A22, A33, where your rows and column both are same, they are called as principal diagonal. Okay, let's look at this. This is the principal diagonal. Now if you can see here, this is a square, this is a square you are forming, Okay, if the elements are 0 in the lower, then it is called as, that means the first, this is 1, so if this is 0, then also this is 0, then this matrix is called as upper triangular matrix, because lower elements are 0. Nothing but, you see here, you have a square, you have a square, you have a diagonal. The diagonal elements are nothing but 1, 1, 2, 2, 3, 3. If elements are 0 on one side, then it is called the opposite triangular matrix. If on the upper side all are zeros, then it is a lower triangular matrix. If on the lower side all are zeros, then it's called the upper triangular matrix. Now any triangular matrix you have, the determinant is nothing but product of the diagonal elements. That means in this case it is nothing but equal to 1 into 2 into 3, that's equal to 6, and the sum of this is called as trace. We haven't discussed about that. Maybe I'll take a small session on which we will go through the types of matrices, elementary types of matrices. We'll go through that. Okay, but this is properties of determinants. I know it's a little bit exhaustive, but it helps you if you understand the concept why I am applying those transformations. Then you will be more confident to solve the determinant problems. Thanks for visiting. Bye for now. See you in the next video.